Okay, this is chapter 9.3, similar right triangles. The essential question here is, how are altitudes and geometric means of right triangles related? What you will learn in this section is how to identify similar triangles, solve real-life problems involving those similar triangles, and use what's called the geometric mean. What does it mean? Okay, let's start this section with a theorem, the sixth one of chapter 9. And it says theorem 9.6, oops, excuse me, right triangle similarity theorem. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So what? So anyway, if you had triangle ABC originally, and you drop an altitude CD perpendicular to the hypotenuse, which was AB opposite this right angle, then you form triangle ACD and triangle CDB. This triangle similar to this triangle is similar to the original triangle. And that's all it means. Okay, so we're going to be using the right triangle similarity theorem soon. Okay, so here it says identify the similar triangles in the diagram. So all we have to do here is identify. So here's what I'm going to do. I'm going to get my pen. I'm going to draw straight lines, maybe this thick and maybe this color. I'll start with red. So let's start with the original triangle. Okay, and I'm just copying it just like this. Okay, and let's put that back and select this and group them and booyah. So there is the whole thing, and then I'm going to name it. So this was S, this was T, and this here is R. And the right angle is right there, angle T. So that was the original. And then I'm going to do it again. This time I'll choose blue. And this time I will go from U to S, from S to T, and from T to U. Okay, that one moved a little on me. Okay, shift, hold that, hold that. Oops, oops. All right, it won't let me group three at a time, so let's group two at a time. Group, okay, and then I'm going to choose this and group these. Okay, and so then I get this. So I'm going to, whoa, that's wonky. What is happening there? All right, so let me fix that. Just 1 second. Okay, so I fixed that. So here we go. So this was here. Bring it down like so. Rotate it like so. And as you can see, it is flipped over. So I need to flip this. So I'll flip it left to right, and then I need to rotate it. So it is like this. Okay, so now I have that tiny little triangle, and let's name it. All right, so SU is the right angle. That's the easiest way to determine what goes where. S was up here, and T is down here. So triangle SRT is similar to triangle SUT. SRT is similar to triangle STU, I should say. Okay, so there's the big triangle, there's the smaller one, and now we have one more. So I'm now going to switch to a green. Let's use this one and this here. And I'm going to go from here to here. Up to you. It's up to you whether you do this or not. All right, so let's see. I need to just move this up a little bit. Shift this, and group, and then this, and what I just grouped, and group, and see if that worked. Okay, so there it is. But that needs to get flipped. Flip left to right, rotate, and there we have it. We have three triangles in a row. This one's not quite as neat. They weren't touching, but this would look like that, and that would come down like that, and that's the right angle. And where did this come from? Well, U was the right angle. T's up here, and this is R. Okay, so if I name the first triangle, then I'd say triangle RST is similar to triangle. Well, R is my smallest angle. Here it would be TSU is similar to triangle RTU. Okay? So RTU is similar to RST is similar to TSU. So there you have it. Those are the three similar triangles in this diagram. Now you should be able to do problem numbers 3 and 4 in your exercises. Okay, so example 2 says modeling with mathematics. A roof has a cross section that is a right triangle. So the cross section's right here looking at the house. Think of cutting a house in half like this and looking at its roof structure. That would be a cross section. The diagram shows the approximate dimensions of the cross section. Find the height of H, the roof height. Okay, so what we see here is this side of the roof and this side of the roof meet at Y to form a 90-degree angle. And that is my red triangle here. This one here. So I'm going to make these all look the same. So if I rotate this and stand it on end like so, then it's going to look like what the book did. So here's my big triangle, the whole roof. This is one part of the roof. This is the other. And this is the horizontal piece with the ground. Okay. And then this piece was here. So I'm going to bring this down. I'm going to rotate it like so, but it has to get flipped. Like so. So there's my other triangle. They are similar. Then I finally bring this piece down and I'm going to flip that one. And so now all these triangles lined up appear to be similar. Different shape or different sizes, same shape. Now I'm going to name these. Now I can name them just using one letter but in the in the diagram up here, just keep in mind that this right here, I can't call angle Y by itself because there's three angles at that point. Okay. But once we move them and separate them, then we can. So the green one was here. So Y was up here. The 90-degree angle was W, and this is X, and this is the 90 degrees. So I'm going to mark these 90 degrees, the smaller acute angle with one or two arcs, and the bigger acute angle down here at the base, one arc. I'm just trying to copy what the book is doing. So this is one arc here. This would be two arcs, and this is the right angle. This is a right angle, one arc, two arcs. Now remember, when triangles are similar, their corresponding angles are congruent. So if this angle right here was 30 degrees, this is 30 degrees, and this is 30 degrees, and this would be 60 degrees, this would be 60 degrees, this would be 60 degrees, and the three right angles are all 90, obviously. Okay, so now I need to name the blue one. So the blue one was right here. So the 90-degree angle's down at W. So it's just flipped over from this one and rotated. So this over here, up here, is Z. And then this down here is Y. So it goes like so. And then this triangle is the original, the whole thing. And it's upside down and rotated. So Y was my 90-degree angle. Z is up here. And this is X. Okay, hopefully you can follow that and picture it, rotated and flipped. Okay, now I'm going to label all this stuff up with my gibbons. So in the little triangle, the green one, so let me just highlight that so you know where I'm looking right now is right here. Okay. The long side here, the roof portion, was 3.1. The little piece WX right here, we didn't know because it's a portion of this 6.3, but they didn't tell us what it was. And this is our height. All right. And then now let me switch to blue so you can focus on where I'm getting this stuff from. Here's the blue triangle. Here's where it came from. So the hypotenuse, because this is a right angle, the hypotenuse is 5.5, which is right here. The height is WY. See the H there? That's down here now. Okay. And now let me erase that. And I don't know WZ because it's a portion of 6.3. We don't know how much. So we're not going to answer that right now. And finally, the red, the whole thing, that's the easy one. That is going to be, the hypotenuse is down here. This is 6.3, 3.1, and 5.5 over here. Okay, so there's everything marked up. So now I can say, well, what do we know now? Triangle. And I'm going to call this WXY is similar to triangle. Now I started with the 90, so I start with the 90, W, but then I went to the single marker, which is Y, and then up to Z. So WYZ. Let's see, WXY, WYZ, and then it should be is similar to Y. Oops, forgot my triangle symbol. Triangle, Y. And I went from W to X, which is 90 to the single arc. So Y to X to Z. Okay. So whatever you name the first one, you better name the rest with corresponding pieces. So there is my statement showing that the three triangles are similar because of the similarity theorem, 9.6. Whew. Okay, so now what I want you to focus on is this triangle has one known and one unknown, actually two unknowns, but one we're calling H. This one has one known, one unknown we didn't even name, and this one we named H, but we still don't know it. This one we know all three sides. So when you are doing a similarity setup to find proportional parts, you have to focus on using the one triangle that has everything and one that has a piece lacking. So that's, I'm going to focus on these two. I'm not going to use the green one. All right, I'm trying to find YW or WY. So I'm going to say WY over, so WY over YZ. So I'm going to say that equals, so I went from 90 to one arc. So 90 to one arc is YX over XZ, which is my hypotenuse. So I went from here to here and then from here to here. Same with from here to here, from here to here. You have to name them in the right order. Now we substitute our givens. WY is H. YZ is 5.5. And that has to equal YX, which is 3.1, over XZ, which is 6.3. So when I get my calculator out, okay, I'm going to cross multiply and I'm going to get 6.3H equals 5.5 times 3.1. I'm just showing all my work. 6.3H equals 5.5 times 3.1. Enter 17.05. Divide by 6.3 to find H. These 6.3s will cancel, and I get H equals 17.05 divided by 6.3. Enter. And I got approximately 2.706. So I'm going to make an approximation. I better say it is approximately. If you round, it's not equal. So H is approximately 2.7 unit of measure meters. So the height is 2.7 meters. So there is the answer to this question. Okay, hopefully you understood that. And so now you should be able to do problem numbers 5 and 6 in your exercises. Okay, using a geometric mean. Okay, so there's a new vocabulary word, the geometric mean of two positive numbers, A and B. Okay, they have to be positive numbers, A and B, is the positive number x that satisfies the ratio a over x equals x over b. So if you cross multiply this, you get x squared equals a times b. And then solving for x, you take the square root of both sides, therefore x equals the square root of ab. So we'll probably be using this more so than any other, but we can use all three actually, depending on what we were given. Okay. All right. So x squared equals ab, geometric mean. Okay, so here we go. Example 3, finding a geometric mean. Okay, so in this case, we have A equals 24, B equals 48, and the geometric mean formula was x squared equals A times B. So step 1, like always, write a formula. Write the formula, substitute the givens, x squared equals A 24, b 48, and x squared equals, and let me get my calculator, 24 times 48, enter, is 1,152, and then we take the square root of both sides, and that will leave us with x equals, and so I'm going to do the square root of second answer, enter, and I get approximately, so it's not a perfect square, so I got ahead of myself writing equals. Since it's not a perfect square, we have to approximate. So the geometric mean is 33.94 approximately. Okay. Now, if we didn't want to do an approximation, then you take what's under the radical, which is called a radicand, and you simplify it. So it ends in 2, so it's even. So 2 goes into 11 5 times with a remainder of 1. 2 goes into 15 7 times with a remainder of 1. And 2 goes into 12 6 times. Do that again. 2 goes into 5 twice, remainder of 1. 2 goes into 17 8 times with a remainder of 1. 2 goes into 16 8 times. Now it's getting easier. 2 144. Okay, and now that I have a perfect square, I'm just going to stop right there. I have 12 times 12, and I have a 2 times 2. So 12 times 2 is 24, and I still have this 2 left over, so that stays in the radical. So x and is equal. I can still say equal now because I haven't approximated. And the geometric mean of 24 and 48 is 24 square root 2. Okay, but that was approximately 33.94 as it shows on the calculator here. Okay, so that's geometric means, pretty simple. Multiply the 2, take the square root, finito, done. Now you should be able to do problem numbers 11 and 12 in your exercises. Okay, we have 2 more theorems, 7 and 8. The geometric mean altitude theorem. In a right triangle, the altitude from the right angle to the hypotenuse, okay, CD, divides the hypotenuse into 2 segments, AD and DB. The length of the altitude is the geometric mean of the lengths of the 2 segments of the hypotenuse. So CD squared equals AD times DB. Wow, that's cool. Okay. All right, so we're going to get into that. And the geometric mean leg theorem states that in a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into 2 segments. Okay, so CD is dividing AB into 2 segments, AD and DB. The length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse. So CB squared equals DB times AB. CB squared, the height, equals DB times AB. The lengths of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Okay, the hypotenuse here is AB. This is hypotenuse, just so you get this clear. Hypotenuse is that. CB is here, and the altitude is CD. They didn't use CD, they used CB. So what are they using here? They're using CB, and they're squaring it. They're using DB, and they're using AB. The length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Okay, so let's do the next one. AC squared is equal to AD times AB. Okay, so what are we doing here? It's the hypotenuse of this triangle here squared equals the leg plus the hypotenuse of the original triangle. Okay, that's a little bit more confusing. This one's very clear. Okay, the altitude squared is equal to AD times BD. This one's a little bit more confusing, so let's take a look at it in an example. Okay, so here we go, using the geometric mean. So this is a really good example here, showing one way and the other. In this case, we don't know the altitude, but it's X, but we do know the two pieces for the hypotenuse. So just going back real quickly, we're going to use the geometric mean altitude theorem. CD squared equals AD times BD. Okay, so that's what I'm going to say. So you apply the geometric mean altitude theorem, which says, in this case, X squared equals, so the altitude squared equals this piece of the hypotenuse plus this piece of the hypotenuse. Okay, or times, I mean. So it's 6 times 3. So X squared equals 6 times 3. Simplify, X squared equals 18. And to simplify this, we need to get rid of that squared. So we take the square root of both sides, leaving me with X equals, and 18 as a factor tree is 2 times 9, and then 3 times 3. So there's our pair of threes that becomes 1 outside, and the 2 that's left over stays in the radical. So the length of the altitude here is 3 square root 2. Now, if you wanted to get your head around that, what is that approximately? Then you would go 3 square root 2, enter, and it's approximately 4.24. Okay, so there's the answer to this problem. All right, so now on to the next. This one's different. They did not give us the altitude of the right triangle. So this is going to be the geometric mean leg theorem. This one's the one that's a little more confusing. So let's just take a look at what we have. We have a right triangle where we know one leg and the two pieces of the hypotenuse. So we know one leg and two pieces of the hypotenuse. So how about I get rid of these red lines? Or actually, I can get rid of the blue. Okay. So we know this piece, and we know this piece, and this whole thing. Okay. So what we're going to do is, applying the leg theorem, you take the side you don't know here, not the two pieces of the hypotenuse. You take and square. I'm going to use blue. You square this leg. So you take y squared equals, and you're going to take this piece times the whole thing. So it's 2 times 2 plus 5. So y squared equals 2 times 7. So y squared equals 14. To finish this off, I need to take the square root of both sides. So y equals, and 14 is 7 times 2. And 7 times 2, they're both prime, so I can't simplify them. Square root of 14 is the best I can do, unless I simplify or approximate by putting it in this calculator. Square root 14 is approximately 3.74. Okay, So the value of y is the square root of 14 or 3.74. A little bit longer than this piece, but not as long as the hypotenuse. So whenever you're doing this, you have to make sure that this answer is between these two values. Can't be longer or shorter. Okay, same with this actually. 4.24 is between 3 and 6. It can't be longer or shorter than these two pieces. Okay. Now you should be able to do problems numbers 19 and 22 in your exercises. Okay, so example 5 is using an indirect measurement. So it says to find the cost of installing a rock wall in your school gymnasium, you need to find the height of the gym wall, obviously. You need a cardboard square to line up the top and bottom of the gym wall. Your friend measures the vertical distance from the ground to your eye. Okay, the vertical distance from the ground to your eye, which would be right here, 5 feet. That's what they're talking about. Okay, and the horizontal distance from you to the gym wall. So how far are you from the wall? 8.5 feet. So if you're standing out here, your friend measured how high your eye contact is with the wall looking straight ahead, which was 5 feet, and measured how far you were from the wall, which is 8.5 feet. Without getting up onto a ladder and having to go up into these rafters, you can actually determine the height of the wall by using geometric mean. Okay, so what we're going to do is I'm going to just copy this down to here, and I'm going to label everything that we were given. So this is 8.5. This is 5, and we don't know this. So the geometric mean says you take the altitude squared, the height of the right triangle, 8.5 squared, and that is going to equal 5 times x. Okay, so then I get my calculator out and I say, okay, 8.5 squared, enter, is 72.25 equals 5x, divide by x, divide by x. I'm sorry, disregard that, divide by 5, silly. Okay, divide by 5 on both sides to get x by itself. These cancel, and I get x equals, go back to my calculator, 72.25 divided by 5 equals 14.45. 14.45. So that's x. So the height of the wall from here to here is the sum of those two pieces. So this distance right here to here is 14.45 plus 5. So it's 19.45 feet. Okay, so we found the height of the gym wall without climbing. All right, so now you should be able to do problem number 30 in your exercise. Okay, that brings us to the end of chapter 9.3. These are the exercises I assigned. It's a fairly short lesson, so I tacked on a few practice problems. Keep your mind fresh from prior stuff. All right, thanks for watching and have a great day.